Hi, Dale. How's your retirement going?
Now that we're recording.
Fine.
Ah, it's okay.
I'm working on a few projects as a consultant, and it's great. I mean, I get to do all the fun work, and there's no management. So,
That's good. That's fun. Yeah.
Amor, che c'è?
Okay. Good day, everyone. Welcome to the 14th annual workshop on the Energy Efficient HPC Working Group. Torsten and I, on behalf of everyone, would like to welcome you all, and also on behalf of the EHPC Working Group Workshop Committee. It has been quite a many months of preparation towards this, and we're glad you all could join. Very quickly, some logistics. Here's the workshop event website. It is also reachable from the working group website. And this website includes an agenda with session abstracts and speaker bios, and we should be uploading all the presentation materials within a few days times. Okay, again, non-speakers, we'd like to request you all to please mute your microphones and turn off your webcams just to limit shared network bandwidth. And please feel free to use the chat box for live question and answer discussions. Speakers and moderators of different sessions, we request you all to.
Yeah. Well, I mean, the success is the only thing that matters. I mean,
please keep track of the chat box as we proceed. Okay, here's the quick agenda. Today we will be there'll be a quick overview of the status of the working group and updates from the different teams. We will also be discussing, we have an exciting keynote planned, specifically AI, as we all know, has been the buzzword these days. Of course, it is a decades-old field of study, but only recently has there been an uptick of interest significantly. Despite all the potential benefits, though, there is an outstanding concern about the environmental impact. And this keynote talk, we are excited to hear about. It will focus on the carbon footprint of various aspects of scaling the AI technology, right? So both hardware and software point of view. We will also have a guided panel discussion, just titled Net Zero and HPC, which would discuss the different types of emissions by data centers and the relevance to HPC. Again, a very critical topic there. We also have some invited talks, which are also guided and moderated. Next one is HPC data center heat reuse. And the purpose of that session would really be to discuss repurposing wasted heat in order to further improve cooling efficiency. Right? And then on day 2, we would again have a series of panel/invited talks like sessions. The first one will be on water conservation in HPC. Focus there will really be on efficient use of water and the need for future resilience of data centers. Especially focus will be around challenges, lessons learned, and some of the future planning efforts. And then last but not the least, we will have a session titled HPC Modular Data Centers. And really there, the focus will be on experiences and lessons learned in planning, building, and operating an HPC center in a right-sized building and infrastructure built in a modular approach, right? So quite a many exciting talks up front. With that, first session will be an overview of the working group updates. And of course, the speaker is the introduction, Natalie Bates, co-chair. Over to you, Natalie.
Thank you, Sid. Thank you very much. And welcome, everybody. I'm going to have Torsten show my presentation and ask him to flip screens. So welcome. We have more than 200 people registered for this workshop. That's a number that exceeds all prior numbers. We're currently at 66, and I'm sure we'll get more as the minutes progress. So I also want to thank the organizers, Sid, Torsten, and a list of organizers, the presenters and the panelists for your really special contribution. And there's a lot of work that goes behind the scenes to create these kind of events. And I also want to, thank everybody here who's participating. Many of you are already members of the working group, but there's really a healthy number of you who are new to the working group. And I am going to cover some of the ways that you can contribute to the working group in this brief presentation. Next slide. So our vision is to curb environmental impact through increased energy efficiency in HPC. But we are engaging in a new focus. We're expanding beyond energy efficiency to sustainability. In the past decade, and that's how long we've been around, we've focused on measuring and optimizing energy efficiency and conservation of both HPC platforms and data centers. And we've had notable successes, and we should be very pleased with our achievements. But I think now we're ready to shift our laser focus on energy efficiency to the broader scope that includes at least greenhouse gas emissions, if not other kinds of resource consumption. We, the volunteer members of the EE-HPC working group and the broader community, we started our journey to improve energy efficiency by working on measurement capabilities. We have several teams that worked specifically on this. The procurement requirements team came up with very clear directive requirements for measurement capabilities for power and energy of HPC systems and for things like temperature as well. And also we worked with the Green Grid and the Green 500 and the Top 500 on improving their power measurement methodology. So measurement was a key focus. Metrics were another step in this journey. We extended the Green Grid's PUE metric with TUE. TUE accounts for the impact of rack level components such as server, cooling fans, power supply units, and voltage regulators. And also we had a dashboard team. Several years before dashboards were very widely deployed, we recommended the elements of an effective energy efficiency dashboard for HPC centers. Beyond measurement capabilities, which are really key tools for continuous improvement, the EEHPC working group has also worked extensively to encourage the deployment of key breakthrough technologies like liquid cooling. Liquid cooling is key to reducing energy consumption because the heat capacity of liquids is orders of magnitude greater than that of air. We've worked with ASHRAE many years ago to push their limits for warm water cooling. We worked with OCP to define a spec for liquid cooling transfer fluids. We published a guideline for liquid cooling commissioning, another one for defining user requirements of control systems. And we're currently working on a guideline to help sites that are taking the initial steps of moving from air to liquid cooling. We are now embarking on a journey to extend our focus on measurement capabilities, metrics, and in breakthrough technologies on reducing greenhouse gas emissions and key resource consumption. Next slide. So this new effort is starting with the procurement considerations team again. Just as we started with measurement capabilities in the procurement team, we're now working on ideas for sustainability measures and targets. We've drafted some high-level objectives to use during the procurement of any product, whether that be an HPC system or an HVAC system. And we've got 5 high-level requirements defined. One is a basic requirement, should be achievable now. Anytime you ask for a new product, ask your vendor to estimate, at a minimum, estimate the greenhouse gas emissions associated with the product. 2, a stretch goal, one that's available for some companies now, but may not be, should be available in the near future. Use a standardized methodology for your product greenhouse gas emissions. So this is, there are several standardized methodologies out there. Pick one of them and start using it. Innovative in the future, maybe not available today, but should be, is extend beyond greenhouse gas emissions. Start looking at the full life cycle of the product, include water consumption, pollution, ecotoxicity, other sustainability measures. Another future innovative requirement. So besides just measuring it, tell us how you're going to improve. Define a reduction target and tell us how you came up with that target. There's some very good tools available, science-based tools for defining your greenhouse gas reductions. Finally, another innovative requirement we've been focusing on, or one of the objectives in already existing in the procurement considerations document is the use of the concept of total cost of ownership. The Europeans have used this a lot in their procurements. So beyond the other costs, include the cost of emissions in your total cost of ownership analysis.
What are we talking about here?
So next slide, please. What is the EEHPC working group? We are a group of volunteers and our numbers continue to grow. We're primarily from the United States and European countries, but we also have lots of members from, 35 plus countries. We're actually over 1,000 members right now. 50% of our membership are from sites, from HPC sites. 30% are from the vendor community and 20% of academics. What makes us really unique is the blend of both facility and HPC systems. So almost all of our teams have expertise from those two silos. And it's a really unique opportunity for these groups of people to talk to each other. It's free and open membership. Next slide. These are the people, the backbone of the EEHPC working group. They're key to supporting the EEHPC working group teams, and they are the ones who review, approve, mentor, and support the teams, this leadership body. And my thanks to all of them. Next slide. How do we work? So the EEHPC working group is a created task forces, teams, right? They're not meant to be long lasting. We get an idea, we define some goals, we specify a deliverable that can help meet those goals. We create the deliverable. Most of the time it's a white paper, but it can take other forms. And then our intention is to try to hand it off to standards bodies. Standards bodies like the ones I've already mentioned, ASHRAE, Green Grid, OCP, Green 500, Top 500. Those are the kinds of organizations that we try to hand things off to. At times, we're not successful in doing that, and we'll just post our deliverables because, again, mostly they're websites, but they can be other things. We'll post them on our website. Next slide. These are the teams. This is a list of all our teams. The left-hand column are the currently active teams. And, some of them are more regularly meeting than others, but they are all in the process of working still on deliverables. The middle column are teams that had been convened, but are no longer active. So, for instance, liquid cooling specification, energy and power aware job scheduling and resource management, grid integration, liquid commissioning, dashboards, TUE, warm water cooling. Those are all teams that are no longer active. That doesn't mean that we couldn't reconvene them if something came up, but at this point, they've completed their deliverable and are really no longer active. Then we have a list of teams that are potential teams. That list can be added to at any time, but those are the ones that we have sort of in the hopper as potentials. Next slide. Okay, so how can you participate? Visit our website, join a team. So the only way you're going to get regular updates on a team is to join the team, and through minutes, and each of the teams has a website, has a Google site. So you can, get more active by joining a team. At a minimum, though, I highly recommend that you either attend or read the minutes of our general membership meetings. We meet every other month. All the team leads come and give a status on their team progress, what they're doing, what their future, what their next steps are. So all those membership meetings are posted on the website. I highly encourage you to go there and read them and look through them. Also, we regularly participate at both ISC and SC in Birds of Feather. Next slide. Okay, so until the next time I talk to you, which is actually at the end of the day tomorrow, thank you again for coming here. This is the website link and my email. Feel free to call me anytime. All right, Sid, hand it back to you.
Thanks, Stephanie. Okay, this is exciting. Next up, we have Dr. Carol Jean Wu. Thanks again, Doctor, for coming over. Really delighted to have you here. Carol Jean Wu is a research director at Meta AI. She's a founding member and a vice president of ML Commons, a nonprofit organization that aims to accelerate machine learning for the benefits of all. Dr. Wu also serves on the ML Commons board as a director, chaired the ML Perf Recommendation Benchmark Advisory Board, and co-chaired for ML Perf Inference. Prior to Meta or Facebook, she was an associate professor at ASU. She's passionate about pathfinding and tackling system challenges to enable efficient, responsible AI execution. Her expertise sits at the intersection of computer architecture and machine learning. Specifically, her work includes understanding computing's carbon footprint, designing low carbon computers at tech, at Meta, and to minimize computing's carbon footprint. Really, as the first step to quantify life cycle emissions. Also featured at the HIPEAC blog. Dr. Wu's work has been recognized with several awards, including IEEE Micro Top Picks and ACM IEEE Best Paper Awards. She received her MA and PhD from Princeton and BSc from Cornell. Once again, thanks, Dr. Wu, and over to you.
Thanks so much for the generous introduction, Sid. And let me figure out how to share my talk. Okay. Can everybody see the slide deck?
Yes, we can.
Okay, awesome. Once again, thanks so much for the introduction, Sid, and also for the very detailed openings for this workshop, Natalie. It's great to hear all the environmental efforts that this working group has been looking at. Good morning, everyone. It's such a great pleasure to be here and have this opportunity to share with you some of the work in the AI space. And today I'm going to specifically focus on the carbon footprint of AI technologies. As what Sid mentioned, I'm currently a research director at Meta's Fundamental AI Research Group. And prior to Meta, I spent about a decade as a professor, where my research was looking at developing high performance and energy efficient computer systems. A lot of environmental sustainability work that I'm going to share with you today has been influenced by my experience as a computer architect, by my past couple of years developing system architecture at scale, and also during the journey to build the MLPerf benchmark suite to look at how to develop this industry-driven performance benchmark for AI workloads. And today, I'm going to take the opportunity to share with you some of the important trends that I have been observing for the AI workloads, and specifically how we should think about scaling AI in a more sustainable way. And here I meant by taking into account the environmental implications of this particular computing workload. Artificial intelligence, or AI, as what we know, has been driving the overall industry's growth. And we've been witnessing tremendous novel use cases that was enabled by this AI technology. It has been used in scientific discovery. AI has played a significant role in medicine, in commerce, in education, as well as entertainment industry. On top of that, AI has also been used to discover electrocatalyst materials in order to scale the efficiencies of energy storage. For example, with this Open Catalyst project that came from Meta's fundamental AI research. On top of that, AI has also been used to discover protein structures through the AlphaFold project. And that has the potential to revolutionize the entire biological science domain. Finally, through the FarmBeats project, AI has also been deployed by the agricultural industries in order to improve the efficiencies of growing food for the world's consumption. The overall AI advancement has been fueled by decades of innovation in computer systems. Today, microprocessors come with over 1 million times more transistors as compared to the very first one from 50 years ago. That's the Intel microprocessor. And it's already running at 750 times faster as compared to that first Intel 4004. Now, the strong demand on computational performance will require system architects to scale up performance beyond single node systems. At Meta, we are building our training clusters that already compose more than 15,000 GPU nodes in order to serve large-scale training workloads. From throughput perspective, that's already 20 times better as compared to the previous generation. On top of that, we are also seeing a large portfolio of domain-specific accelerators coming to the market. And it is that decades of technological innovation that made computing orders of magnitude more efficient through vertical scaling by improving single node performance, and through horizontal scaling by interconnecting a large number of computer systems together, and through hardware specialization to further scale up the performance and power efficiencies. Now, this impressive technological advancements has democratized the access to information and education. It has many societal benefits. It has increased our quality of life, provide significant economic growth. It, however, also comes with significant energy costs at the same time. Across the entire computing industry, when we start looking at client computing, all the consumer electronics, the telecommunication infrastructure that connects the client devices to high-performance cloud scale computing infrastructures, we found that across the entire computing industries, we collectively produce over 700 million tons of carbon dioxide. And that's equivalent to half of the aviation industry's overall emission. And a significant part of that computing's emissions come from hyperscale data centers. If we take a look at the energy footprint of some of the technology companies, for example, Google, Meta, and Microsoft, what we found is that in the past 5 years, the energy footprint has been growing quite a bit. On the x-axis here, we take a look at the energy footprint requirements from 2017 to 2021, and we normalize that energy footprints at the company level to Meta's company level footprints in 2017. And what we found is that for companies like Meta, we see a 3.8 times energy footprint growth, whereas for Google and Microsoft, it is a 2 to 2.4 times growth. And this is to support the significant growth in the overall cloud computing industry. There are many reasons why we believe that this energy footprints of the computing industry is going to grow in the next decade. First, only half of the world population have internet connectivity. For United States, about 25% of the population still doesn't have home broadband connections. So as more users are connected to internet, we expect energy footprints to grow correspondingly. Second, there are many new use cases that's coming online. AI being one of the most significant ones, I think many of us will agree. And finally, Moore's law has really slowed down. Hyperscale data centers are really optimized in terms of PUE, power usage effectiveness. And so it's going to be increasingly more challenging in order to improve the computing's performance efficiency further. It has been projected that, in fact, the overall energy footprints of the ICT industry is going to reach 7% of the global energy demand by 2030, and that's going to double what we have today. Now, recognizing the significant environmental implications of computing, leading technology companies have made various climate pledges to sort of inspire technology developers and engineers and policymakers to figure out how do we get to net zero by 2030. For example, Facebook, Meta, Microsoft, and Google have all reached net zero for the company level operational energy consumption. And further, all companies have made net zero across value chain climate pledges by 2030. And so there's a lot more that we technology developers, researchers, and engineers can do to innovate to get to net zero for the computing industry. So today, I'm going to use this talk to first look at what is the scaling trend of modern AI computing. And so we're going to use AI as an example here to look at what is the carbon cost for these large-scale workloads. And then we are going to then draw key observations and distill directions that is important to invest in order to scale this important application domain in a sustainable manner. Okay, so I'm wondering if we want to take a pause and then see if there are questions from the audience. Okay. So perhaps we can come back to it if there is not a question right now. Yep.
I'll keep track of the chat box, Dr. Wu, and let you know as questions arrive. Thank you.
Thanks very much. Okay, cool. So let's take a look at what is the scaling trend of AI technologies. At the very high level, there are 4 major steps across the AI model development cycle. There's data preprocessing, experimentation, model training, and once model is meeting the desirable accuracy target, then we perform additional efficiency optimization, then deploy the model to serve trillions of predictions worldwide. Over the past 2-year time frame, what we have found is the data volume for AI has doubled. And this has been driving significant infrastructure growth demand in the sense that data ingestion bandwidth demand is growing as well. And also it's reflected on the storage requirements at large-scale data centers. Now, to learn these valuable information from the ever-increasing data volume, it also means that model sizes are increasing. And during the same 2-year time period, we see the model size has grown by 20 times already into the terabyte magnitude. And then all of these boils down to significant growth in the AI infrastructure capacity. For both training and inference infrastructure capacities, we also see more than 2 times growth within the same 2-year time period. Now, given these exponential growth and scaling trend of modern AI use cases, a couple of us were quite interested and also worried about the amount of energy that a production scale machine learning task could consume at meta scale. So we asked the question, how much carbon emissions does training and industry scale machine learning tasks will produce? And our first step is to really understand the lay of the land of AI's carbon footprints. And by answering this question, it kickstarts our green AI journey. We start by measuring AI's operational carbon footprints by using the following equation. This equation is something I believe that all the electrical engineers, mechanical engineers, and technology developers would agree upon. We measure the operational carbon footprints as a product of the following high impact factor. First, we take the execution time of model training or inference, and then we multiply that by the number of processors that we used for example, model training time. And then we also take into account the power consumptions for the IT equipment that was used for performing the computation. So for example, we use more than 2,000 GPUs to train the state-of-the-art language model Llama that for a month's time frame, the training time in this case would be 30 days multiplied by the go figure out the corresponding hours. More than 2,000 GPUs in this case, we then also take into account the host system, the CPU, and the networking requirements, as well as storage nodes. And then we then approximate the power consumptions per processors that was consumed during model training. Now, this power consumption can be measured using power performance counters. It can be measured using power meters, or we can also approximate the worst case scenario by using the thermal design power for each of these IT equipments. On top of that, we also take into account the all the additional overhead of data center operations. So for example, by taking PUE of data centers of 1.1, we then take into account that 10% additional overhead coming from facilities. And then finally, the carbon intensity of electricity that we use play a significant role in the operational carbon footprints of AI as well. And so we then go figure out what is the average carbon intensity of the power grid that our data center draws the power from. And then using this equation, we then report the carbon footprints of our model training. Now, when thinking ahead about how to reduce the operational energy and carbon footprints of AI, reducing each of these factors will directly translate into carbon emission reduction. Okay, so this is what we found. On the x-axis here, we are looking at 6 most important machine learning models that are representative of Meta's production task, ranging from universal language translation model to various deep learning recommendation and ranking use cases. On the y-axis are the carbon footprint estimates using the previous equation. And what we found is that training a modern language model for Meta product will produce 45.2 metric tons of carbon emission. This is equivalent to approximately 5 US homes energy usage for 1 year. Whereas training a DLRM or deep learning recommendation model will produce carbon emission that's 9 times higher. Now, once model is trained, it is further optimized for production deployments. And so there is the additional operational carbon footprints from inference prediction phase. And so you see, depends on which workloads, there is the additional carbon footprints coming from model inference. What's interesting is that for language model, the ratio between training and inference footprints is about 1 to 2, whereas for DLRM use cases, the training inference footprint is about 1 to 1. And the exact breakdown is determined by how often a model needs to be retrained, depending on the dynamic characteristic of the data set. Now, seeing the large resource footprint requirements of AI, I guess one of the things that we do regularly within Meta is to investing in significant hardware software optimization efforts. And so here, I'm going to take the language translation task as an example, the first workload from the previous slide, and then share how hardware software optimization can help drive down the power footprint requirements of this language model. We start with the CPU server as a baseline. We can improve the power efficiency by 6.7 times through various application level memory optimization. For example, we figure out frequently accessed embedding vectors. We can cache these embedding vectors on the faster memory of the multi-level memory hierarchy. And we can also make some of these pre-computed embedding vectors to be shared across different application use cases. That's going to give us pretty significant power footprint reduction. In addition to software caching, we also look into how to deploy these language model onto GPU-based AI hardware. By doing so, it helps us unlock an additional 10 times power efficiency improvement. On top of that, there is additional numeric optimization opportunity if we leverage the low precision data types on GPU. And then finally, there is algorithm optimization that we put in order to get that additional 5 times power footprint reduction. Overall, through the combinations of platform level hardware and algorithm co-optimization, we can improve the power efficiency by more than 800 times. On top of that, on top of the caching, low precision inference optimization, for model training, there is all the additional opportunity if we can parallelize our model training further. So on the x-axis here, I'm showing how various parallelization strategies used for large language model can help. So from the fully sharded data parallel FSDP baseline all the way to tensor parallel and also data distributed parallelisms for model training. On the y-axis, I'm showing the normalized training throughput. And the different bars in the figure will represent the training throughput on various training systems. Blue for NVIDIA's A100 GPU. The red and yellow are some of our projected throughput for next generation training systems. So what we found is that on current generations of training infrastructures based on the A100 GPUs that we have at Meta, the best parallelization strategies is to use tensor parallelism and distributed data parallelisms for training this language model. And this is going to give us the highest training throughput improvement. Now, on top of that, if we can then deploy higher performance training hardware, that is going to give us all the additional throughput improvements. In this particular case, the improvements that we'll benefit from is from 1.12 to 2.5 times, for example. Okay, so there is then the efficiency and performance improvement that's going to translate into carbon reduction. And so one of the first steps that we do is to focus on efficiency optimization through hardware software co-design. And we do this iteratively, regularly over time. And one of the interesting things I will also highlight is that there's a lot that algorithm can help in the sense that our Meta's latest open source model, Llama, can learn information in a much better way, in a more efficient way. And so when we did the carbon impact assessments for Llama model training, we found that this particular model is much greener in the sense that it can train 24 times faster using much less resource as compared to the state of the art in the particular cases, the GPT-3 model training. Now, while this iterative hardware software co-design process is important, it helps companies like Meta to achieve impressive power footprint reductions. For AI, this improved efficiencies will immediately translate into more uses. This is a phenomenon that's also known as the Jevons paradox, which says when the use case demands are high, efficiency improvements can encourage higher uses, and that will lead to even higher resource consumption overall. So despite the fact that we achieve higher performance efficiency, the overall power footprints of the machine learning task continue to rise over time. In this particular case, by 18% for this language translation model. What this means is that across the many dimensions of AI, the growth trend can easily outpace the efficiency improvements that we put in place at scale. And therefore, despite the opportunities for optimizing energy efficiency and to reduce environmental footprints at scale, we must remember how to address the current scaling trend of AI beyond efficiency optimization. Okay. So far, we have focused on operational energy footprint. As you remember in the introduction that Natalie mentioned about all the additional components that can come in addition to operational resource consumption. So we are also going to look at what are some other components from carbon footprints perspective for AI. And in this particular case, we are going to look at the embodied carbon component. And to do so, we are going to use the lifecycle analysis or the LCA methodologies that is commonly used to analyze a product's total lifecycle emissions. In LCA, there are 4 major phases from manufacturing, transport, product use, and recycling phase. Here, the energy footprints of AI computation or operational carbon footprint that we have been looking at is coming from the product use phase. And this is the operational carbon footprint that we've been talking about. On top of that, there is the embodied carbon footprint. This is the carbon emission produced when building infrastructures specifically for AI. So this includes constructing new data centers to enable AI computing. It also includes all the additional carbon footprint to manufacture the IT equipment for AI computing. So all the GPUs, the corresponding network infrastructures, as well as the data storage capacity that were put in place for AI data storage and ingestion. And so having a peek at AI's training's operational carbon footprints just a few slides ago, I guess the question that we have is, what is the proportion between embodied and operational carbon footprints? Are we missing a significant component when we try to look at reducing AI's carbon footprint, or what's the lay of the land like? And the figure that I'm showing on the slide here is basically all the hardware equipment that needs to be put in place to enable state-of-the-art AI technology exploration. So this is a photo of our Meta's latest research supercluster. And that's where the embodied carbon is going to come from. Okay. So about 2-3 years ago, when we started trying to answer the question of what is the life cycle emissions for the training clusters, we start actually with the life cycle emission breakdown for consumer electronics. And so this is work that's carried out with colleagues from Meta, researchers from Arizona State and Harvard universities. We start analyzing carbon footprints of computing for various Apple products. Apple does a really good job on sharing their and conducting their environmental footprints of Apple products. And so we examine many environmental footprint data from Apple's sustainability report and found that the manufacturing emissions dominate Apple products. So in this pie chart, we take a look at where carbon emission or equivalent emission is coming from. And it's evident that hardware manufacturing accounts for 74% of Apple's overall emission, of which 33% comes from integrated circuit. And this is including manufacturing the SoCs, systems on chip, the DRAM, and the NAND flash that's in the Apple product. In comparison, operational use of Apple devices accounts for 19% of the overall emission. Okay, so that's the story about client computing. For data center, we also take a look at what the breakdown is like. For data center, the manufacturing and operational carbon footprint is roughly an equal split. So for both domain, cloud computing versus consumer electronics, and manufacturing carbon footprint is a pretty significant portion. So now to get back to AI's overall carbon footprints, we then develop a model for us to estimate the embodied carbon footprint of AI. What we did is we take all the IT equipment required by model training, and then we figure out the model training time amortized across the life cycle of the hardware equipment, and attribute the portion of embodied carbon footprints to that particular AI model training. The lifetime estimation, for example, for CPUs is about 3 years, and now it's about 5 years. And so we take into account what is the expected lifetime of the equipments that we have in data center. And this is what we found. Embodied carbon is a substantial part of AI's overall carbon footprint. So across the same 6 machine learning workloads that we were looking at, embodied carbon introduced about 50% higher carbon footprints on top of the operational carbon footprint. Now, we also want to recognize that there's many sustainability efforts that Meta has put in place. And what that means is that operational energy and carbon footprint has been neutralized by all the renewable energy credit that Meta has procured over the years. Quantifying the exact environmental footprints of technology is a very complex process. And this is our sort of first attempt to just take a look at what is the breakdown like. And we want to use this to guide the optimization effort going forward. And so in the next part of my talk, I want to then share some of the directions that I believe our community should focus on developing for the next decade. Specifically, on the AI system development front, we must focus on developing environmentally sustainable systems and infrastructure. And there's also interesting opportunity on carbon efficient AI algorithm front. And on top of that, when we start scaling our computations onto data centers at different geographic locations, we can then start exploiting the nonlinearity of the relationship between energy and carbon emission factors. And then finally, a lot of AI is happening at the edge. And so how should we think about the role of green energy when we start running computations in a distributed setting? Now, while my talk is focused on AI, I think there is a lot of common ground that you can take back to apply that onto the workloads that you are working on. So first, let's talk about designing environmentally sustainable system. On this particular directions, been thinking what are some low-hanging fruits for technology developers after seeing that carbon bottleneck of computing has shifted from product use phase to system hardware manufacturing. And one of the opportunity I saw is something we can already work on is deploying or developing technology, the virtualization technology. And why do I say that? So a couple of years ago, when we start analyzing the utilization of AI accelerators, in this particular case, GPUs, what we found is that while many GPUs are running at 80 to 90% utilization level, there's a pretty large hump of workloads that's utilizing GPUs at only 30 to 50% utilization level. And so what this is telling me is that there's a lot of opportunity that we can amortize this upfront embodied carbon cost if we can maximize utilization for systems that's already deployed. On top of that, we can also look at how to prolong system hardware lifetime as much as possible to amortize the embodied carbon cost that's already come with the system hardware. And when we start extending system hardware lifetime to amortize that upfront embodied carbon cost, we will start observing that the failure rates of various system components is going to increase due to wear outs, for example. And some of these hardware failures can be mitigated with hardware redundancy, while other errors can be masked through new software solutions. And so now when we start thinking about developing next generation software systems, we should take into account the effects of aging hardware. How do we extend the lifetime of systems that's already deployed a lot further than what we currently do? Okay. Now, that's the sort of the low-hanging fruit from cloud computing side of things. What does the client computing landscape look like? Here, we take iPhone as example. During the decade, we see that iPhone are seeing 1.6 times reduction in its operational carbon footprints, while the manufacturing footprint has increased by 3 times. And this is because a lot more advanced hardware architecture has been deployed in the newer generations of iPhone. And that is going to result in higher hardware manufacturing cost. And this carbon bottleneck shift is primarily driven by the use case, where for client computing, we care about low latency, low power, and low energy consumption, particularly at the product use phase. And so what is less known is that this operational efficiency gain come with significant upfront embodied carbon cost, as more domain-specific accelerators and specialized hardware are being incorporated into the Apple hardware, right? And without doubt, AI is one of the most significant application driver for this increase in embodied carbon. And this is why I'm really excited about coming up with a way to help our community to design computer systems by taking into account carbon as a design principle. In the past, we have been designing computer systems with performance in mind, with power in mind, with area as a proxy for cost in mind. And we have all sorts of design tools that help us to figure out how to make the trade-off between performance, power, and area. We haven't had a metric and tool that can help us figure out how to design sustainable computer systems and specifically to minimize carbon footprint. And our first attempt to do that is to develop this tool called ACT, Architectural Carbon Modeling Tool, where we take into account the manufacturing characteristics for semiconductor as input to our tool. We take into account the software and hardware characteristics for workloads that we are designing hardware for. And then the tool is going to then produce some estimates for embodied and operational carbon. With this particular estimation on the total life cycle carbon estimates, then we can then have formed this iterative design process such that the tool then can help us discover the hardware design point that comes with minimum carbon footprint. Now, hopefully this tool is the first step to enable our communities to design computer system solutions by putting carbon as the first design principles. The tool itself has been open sourced through the Facebook research website. So I want to sort of put this on your radar to take a look at the design of the tool, to use the tool itself, or if you find any area for improvements, also join in the efforts to further improve the tool such that our community can start looking at how to put sustainability as the first design principle along with performance, power, and cost. So looks like I'm running out of time, so I'm going to skip this next directions on carbon efficient algorithm and then move on to what are some optimization at scale opportunity when we start looking at carbon aware data center management. As what I have mentioned before, Facebook Meta has investing in significant renewable energy infrastructure at power grids where we have data centers located. And this is a great move because cloud users can benefit from economies of scale by running their computations at hyperscale data centers. And some of the public cloud operators has also made available the carbon intensity of energy, so then the users can decide when they want to run their workloads, have computations to happen at low carbon intensity time of the day, for example. Now, this is what is interesting here is that in this work, when we started looking at this carbon aware data center management project, we found that reducing operational carbon footprint sometimes comes with significant embodied carbon implications. And what we found is that a more cost-effective solution must consider the role of both operational and embodied carbon. It's important to optimize for both as opposed to just operational carbon footprint. And here are some of the examples I will give on this front. So on this particular work that was published in ASPLOS 2013 this year, we start looking at what is the design space like between operational carbon footprint and embodied carbon footprint when we start considering solutions such as renewable energy investments, energy storage using batteries, or on top of that, there's also carbon-aware scheduling as a lever that we have in the space. On the x-axis are the embodied carbon footprints. On the y-axis is the corresponding operational carbon footprint of the data center. What we found is that renewable energy can help us drive down the operational carbon footprints with smaller increase in embodied carbon. Now, carbon-aware scheduling can continue to help us drive down operational carbon, but then now, in order to get the remaining % of operational carbon footprint to 0, it will require us to be innovative by considering storage technologies, energy storage technologies. And the hybrid solution space is the most cost-effective one to reach 100% renewable coverage. But if you start thinking about the optimization space across data centers at different locations, not all data centers are going to, it's not easy to get the operational carbon footprint to 0 across the different data centers. Sometimes it becomes really hard to reduce that last few percentage of, to achieve the last few percentage of carbon-free computing. While I don't have time to delve deeper into the detail, I would like to encourage the audience to just go to a paper to read more about this particular work, and I'll be happy to answer any questions either here or through email, different channels. And then as what I've mentioned, a lot of AI computing is moved to the edge. And so how should we think about, for example, reducing the environmental implications of computing at the edge? Some of these particular execution environments is a lot more complicated in the sense that the role of renewable energy is not as is not the same as compared to cloud computing infrastructures. And so we are also working on scheduling algorithms in particular to figure out how to further reduce the carbon footprints of edge applications. Okay, so to conclude my talk, we have witnessed impressive technology advancements in the past 50 years, and that has bootstrapped the AI revolution. We have focused the past decades on operational performance and energy efficiency optimization. Now, hopefully in this talk, I have convinced you that the carbon bottleneck has shifted now to embodied carbon. And this is what our community should focus on to figure out how to achieve an environmentally sustainable future by considering the relationship between operational and embodied carbon for computing going forward. If you remember, the title of my talk is about scaling AI computing sustainably, where AI is the most critical application driver. What that means to me is that we must pay a lot of attention between the scaling trend of AI data, model sizes, infrastructure capacity requirements. And if we can reduce the amount of capacity requirements by being more data efficient, by developing more efficient learning algorithms, we should focus on that, solve the problem at the source. On top of that, we should also keep in mind the life cycle of AI systems by taking into account the operational and embodied carbon footprint. We need to minimize the total life cycle emissions of computing. And this is going to require a lot of innovation. First, we don't have very well-defined metrics or accounting methodologies for carbon emissions. And this is very different from performance measurements, power or energy modeling that our community is very familiar with. Thankfully, there are some initial efforts. In the introduction of the workshop, I heard the mention of OCP. This is an effort that I'm very excited about. OCP has kickstarted the sustainability initiative to help developing a environmental footprint reporting standards, such that customer-facing companies can now have a way to ask vendors to provide environmental footprint estimates for the product that they are selling, right? And it's very powerful for customers to ask that question. We should keep on asking, and then have vendors to report the corresponding environmental footprints, which then can be helping the purchasing decision process. On top of that, at FAIR, we also developed two important tools to enable sustainability-driven design for computing. One is ACT, which I talk about. This is the architectural carbon modeling tool for computer system design. Second is Carbon Explorer, which enable us to figure out the trade-off between data centers' operational and embodied carbon footprint. On top of that, I believe there is a lot of research that needs to happen to help us develop a new computer system stack, such that we can have an easy way to minimize carbon footprints of computing going forward. And then finally, what I envision is the interplay between computing and the sustainability community. There's a lot that we are looking at how to reduce and improve the sustainability aspect of computing, AI being one of the most significant workloads that we've been focused on. But there's also the other direction. How do we use computing technologies to improve and fight the climate change that the world is witnessing right now? On top of that, I think, one of the most frequently asked questions during my sustainable AI talk is, what does the market look like? Like, how do we incentivize sustainability work by building to have an economic incentive in mind? So that's something I believe that our community should think really hard about, because this is like one of the best way to drive growth. Okay, so if you are interested in some of the work that I get to talk about in this talk, here are some pointers for you. And then I also want to give a big shout out to all my colleagues, collaborators who I work with to carry out the work that I get to share with you today. Thanks so much for your attention, and I hope there is still time for some discussion.
Thank you so much, Dr. Wu. This was a fantastic talk with quite many pointers to different research. There's one question in the chat box. After that, I'd also request other folks, feel free to unmute, go off mute and ask your questions. The question on the chat box reads, how do you account for carbon and energy footprint for models that don't make the cut at Meta, especially models that are dropped after experimentation? Clearly, there must be many models at work that don't show the expected gains.
Yeah. That's a great question. I think what that means when you start interpreting the carbon footprint characterization that I shared during the talk is that there is a lot more that can happen in terms of research exploratory work. There's a lot of research idea that does not make their ways into deployment phase, and therefore all of that can add up. And so it's possible that AI's overall carbon footprint is higher than what I share with you. And that's one dimension. Second is, I think scale really matters. While I share with you the per model carbon footprint estimates, some of these models are trained frequently. And so depends on the training frequencies, that number can add up quite quickly. However, any optimization efforts that's put in place to reduce the per model carbon footprint is also going to be reduced with that scaling factor. So those are like some of the things to think about. How to, which optimization directions you would like to focus on. Yeah.
Thank you. A question from Natalie. Does Meta have large-scale, high-performance computing systems that might run a single application, similar to what we might see with supercomputers running grand challenge applications?
Interesting. I guess the most prominent one that I work with on day-to-day basis is AI, like model training. Like these models are becoming really large. And so, for example, Google has talked about their pathway distributed system. Their vision is to have just one single model, foundation model, that is trained on these their TPU fleet, which I think the corresponding setting will be like the GPU-based supercluster that will be used entirely to train a foundation model. And so from that angle, I think it's equivalent to a single application. It's a single application, large-scale distributed system that industry is developing.
Thank you. And another next question is, what is the carbon footprint of batteries for storing energy?
Yep. So when I think this question is related to our work in Carbon Explorer, we look at the embodied carbon cost for each of the solution that we care about. And one of those particular lever that we have is battery. So what we end up doing is we take a look at the life cycle analysis report by various different battery technology. And thankfully, they are company that would share the environmental sustainability report for their energy storage technology. And so we then use that number in our design space exploration tool. And I think this is something I guess we should pay more attention to, is not only that we want to ask for the environmental footprint data for computing systems, we want to do that for all the energy storage technologies that we care about as well. Take that into account when we make the design decisions about and provision the energy storage solution, renewable infrastructure investments, and all that. So I guess the TLDR is that we use the publicly available number in the study.
One more question. How does Meta handle processors at their end of life cycle? And what steps are being taken to pursue the circular economy that was mentioned?
This is a great question, and a lot of conversations on this topic is actually happening through OCP system. OCP, the Open Compute Project Consortium. So first, what does Meta do for CPUs and IT equipments that we recycle from the data centers? I think one of the options that we consider is to find the second market that would then use the IT equipments that we recycle from the data center itself. My understanding is that for disk HDD, it's very hard to completely erase the data from these storage devices. And so the state-of-the-art approach is to just destroy the disk drive entirely. And I believe that there's a lot of conversation through the OCP forum on how to securely erase data from disk such that that can go into the second market. And when we start doing that, it's going to extend the life cycle of some of these IT equipments. And therefore, people can then figure out how to build a circular economy to create economic opportunity out of the, not the most recent IT equipments, but then, they are market that may actually benefit from using them. On top of that, I think making our design a lot more circular than what we have today is also going to be important. We don't want to just recycle or destroy the system entirely, because one of the component is not working, one of the components failing, right? We want to be able to have different upgrade opportunities at the component level. And that's a really sort of effective way to prolong the lifetime of computing equipment in a data center scale.
Thank you so very much, Dr. Wu. For other questions, I'd urge everyone to please send out emails. Feel free to send it out to the organizers and we can aggregate it and send it to Dr. Wu. And once again, Dr. thank you so very much for your time and for this fantastic talk.
Thanks so much for having me here.
Okay. Moving on. The next session is quite interesting. Really, the focus is on discussing different type of data center emissions, and to that effect, the relevance to HPC. This session will be a panel-driven sessions / a few interesting talks, and will be moderated by Jenna Valpogel. Jenna is an operations manager within the Utilities and Infrastructure Division at Los Alamos. She works with a team of 6 to implement EO and DOE regulations, including the Site Sustainability Plan, Zero Emissions Planning, Energy and Water Efficiency, and Project Planning for the division in collaboration with other programs, including HPC. Over to you, Jenna. Thanks for driving this.
All right, thank you. Can you all hear me?
Yes, we can.
Cool, awesome. Well, welcome everyone. Thanks for joining us. We have an awesome panel. So I'm gonna go through some quick introductions and then kind of tell you what we're gonna talk about today. And then we'll start asking questions. So we have a couple canned questions ready to go, and then we're hoping that you all are vocal and will ask us lots of questions too. So for introductions, I'll start with Otto. He is from NREL and he is a principal engineer. His work, he really does a lot of design, construction, all that work with energy efficiency, especially looking at laboratories. And he also started our Smart Lab program, or one of the founders of the Smart Lab / Lab 21 program. John is over at Berkeley. He is the Chief Sustainability Officer, and he is responsible for implementing sustainability across the laboratory in relation to climate, energy, waste, and water. And then Jesse is from LANL, and he is our net zero program manager. So he's the one taking on all of our net zero stuff here at LANL and working on that across the board. So real quick, before we jump into net zero and HPC, I wanted to just quickly talk about the 3 different scopes of emissions, because that's one of those things that if you're in the HPC world, you might not know what those 3 different scopes are and how we break them out. Let me see, I'm going to share my screen, hopefully. Maybe I don't use Zoom very much. Maybe I can't, that's okay. I think I'm just on the browser version. But I can send out this graphic. There's one on EPA that's really good. But basically your scope 1 emissions are all of the emissions that come from the site. So there are fleet vehicles and they are our facilities. So anything that comes from a facility or vehicle on site is our scope 1, and those are direct emissions. Then scope 2 is another one of ours. So that's all of our purchased electricity. So, oh, perfect. Thank you. Yeah, this is such a good graphic. So yeah, and then our scope 2 is all of our purchased electricity. So everything that we buy, whether it's solar, whether it's coal, all of that purchased electricity goes within scope 2. And then scope 3 is the fun part. And that's one that I think is a little bit all over the place, and we're still trying to figure out in the sustainability world, but it's pretty much all of our purchased goods. So anything that we purchase and bring on site, including any embodied carbon, which we were just hearing about, any sort of waste generation or operation, wastewater treatment, employee commuting, business travel, any leased resources. So you can kind of see all of the different things that are in scope 3. So that's kind of the one that's the hardest one for us to really, I guess, quantify at this moment. So those are kind of the 3 different scopes. Figured we go through that quick just so you have a little background while we go through the rest of the talk. All right, thanks. All right, so like I said, we have a couple questions ready to go, and then please ask questions in the chat if you have them, and we'll get to those too. We want to hear from you all on what you want to hear. So the first thing we'll do is I'm going to ask each panelist to kind of just give an overview of their site, just in case you're not familiar with it, and then kind of what they're doing within their HPC operations to reduce any of these emissions. So I'm going to start with Jesse from Lannel.
Great. Can you hear me okay? Great. So as Jenna said, we're both at Los Alamos National Laboratory. For those that aren't familiar with us, we are, and haven't seen the Oppenheimer movie this year, we are the senior laboratory in DOE, founded in 1943. We're in Northwest New Mexico, kind of north of Santa Fe. Our site is fairly large, so we are 40 square miles and somewhere around 10% of DOE's total electricity. And within that, about a quarter of our electricity is just to HPC. So it's a big part of our usage and our consumption. And so we're spread across 40 square miles and have 900 some odd buildings. So there's a lot going on at Lannel. We're the nation's only plutonium center of excellence, and we're doing a lot of building right now, building somewhere around 1 million net square feet over the next decade to meet our plutonium pit mission. And so with a lot going on, it makes it challenging, but one of the big focuses for us over the next decade, and one of the most immediate goals from the Executive Order 14057 is 100% carbon pollution-free electricity by 2030. And so Los Alamos is unique in that we are essentially our own utility. We partner with Los Alamos County as part of a power pool in the NNSA, and we have a great, ability to influence our power procurement on the site. Our scope 2 emissions, like Jenna mentioned, is our purchased electricity represents about 60% of our total emissions. So in terms of like scope 1, 2, and 3, as it relates to HPC, we're really focused on the scope 2 emissions at this point in time and getting those down over the next decade or so with more carbon pollution-free electricity purchases. We're also trying to ramp up our monitoring and metering over at our high-performance computing facility and measuring PUE a little bit better. We do some, our newest platform just came online. And so with each platform, we get a bump in performance, but also a bump in power consumption. And so trying to manage that using free cooling as much as possible, using warm water cooling, on-chip cooling is really a big part of that. But we do reach kind of fundamental limits of the facility that we're in. So planning for the next generation of computing facilities and making those as efficient as possible is a big part of what we're doing on the sustainability team. And then in terms of scope 3, as Jenna mentioned, it's something we're still trying to wrap our heads around. Like, we know that our operational energy and carbon is really huge, but we don't really know yet, what it is in terms of our, embodied carbon of our data center. So it's something that we really want to dive in and would love to hear from other folks here about their approaches to measuring scope 3. I think right now, we have an older building and new equipment that gets cycled through. So there's definitely some balance into how we incorporate that into our total emissions. But I'll hand it back over to Jenna.
Awesome. Thanks, Jesse. All right, Otto, do you want to go next?
Sure. Yeah. Thanks, Jesse, and thanks, Jenna, and thanks to everybody attending. NREL is another one of the national labs, and Berkeley will go next. We're actually quite a bit smaller than Los Alamos, which is huge. But we're still 3,000 people or so, and we're still about 50 years old. Our mission's very different, and we focus on just energy efficiency and renewable energy. It turns out, even though we're quite a bit smaller, we still do a fair amount of high performance computing. And our high performance computing is about 50% of our site's energy use and water use. So it's still very big. All three of us are actually in water constrained areas. So that'll be an upcoming talk, but water is one of our key metrics. We were early adopters of warm water direct liquid cooling. 2013, so 10 years ago, we were one of the first sites to go back, if you want to use that term, back to liquid cooling. And our strategy was, and still is, to use as warm water as possible. And I'll talk about some reasons why. And then to reuse some of that warm water to do some of our heating in our building and our campus. This is going to be an upcoming topic about heat reuse in this panel, or in this session, not this session, but this conference. But it's one of the ways that we can take our, Jenna talked about scope 1, 2, and 3 emissions. Data centers are very minimal scope 1 emissions, very little on-site emissions. But if you can reuse the waste heat to offset some of your fossil fuel-based heat, it's a way that you can reduce your scope 1 emissions sort of indirectly with your data center operations. A couple more things and I'll turn it to John, but we do actively monitor all the performance metrics for our data center. PUE, we actively monitor and have been running at a PUE the past decade of 1.03, so very good. We also do monitor energy reuse effectiveness, that ERE, and run at an ERE of about 0.9. And then we also monitor water use effectiveness, which I'll talk about in the water talk. Just for scale, our data center has a 10 megawatt ultimate capacity. It's about 10,000 square feet. Our current load is about 4 megawatts. And it's we are primarily using HPE/Cray direct liquid cooled hardware. And I'll stop there and pass it to my colleague and friend, John. I don't hear you, John.
Hear nothing.
Try something else.
Yeah, that worked.
Does that work?
Yeah, I can hear you. Can everyone else?
Yep.
Yes.
Yes, we can hear it.
Okay, I moved to another set of speakers. So thanks, Otto. I come from Lawrence Berkeley National Laboratory, a multi-program Office of Science laboratory. Our primary HPC system is called Perlmutter, a GPU dominant system associated with NERSC, National Energy Research Scientific Computing Facility. Similar to both Jesse and Otto, about a quarter to a third of our site energy consumption is associated with NERSC. Most recently, the whole center has a load of about 4.5 megawatts. That's down from 7 megawatts because we retired a previous system called Cori back in May. I'm a sustainability practitioner, so when I think of net zero, I think of making a plan. And the first 3 building blocks of most infrastructure-related net zero plans involve 3 things. So the first is efficiency, slowing the problem down and reducing your energy consumption. The second is renewables, finding ways to source your electricity from non-carbon sources. And the third is electrification, moving loads that were previously served by fuels onto the decarbonized electricity grid. So we've spent a lot of focus at NERSC on efficiency. I would say our 2 primary approaches are kind of institutional approaches. So one is establishing a continual improvement energy and water efficiency team. So just getting all the right minds together, really learning about the systems in your supercomputing center and meeting regularly, whether that be weekly. We used to meet weekly, now we meet monthly to optimize the system. So over the years, we're comfortable in saying that we've reduced the overhead energy consumption of our compute facility, so the cooling plant, by over 40%, just by sort of that focused attention to the systems as they continue to evolve. As well, we're doing a lot of operational monitoring, analytic tools. So much as Otto mentioned, we're doing continuous PUE monitoring, WUE. We're at a PUE of just under 1.06. Really what we have done is taken analysis that we've done over the years and translated them into operational tools. So we're often looking at like the energy consumption of our cooling plant in a scatter plot as a function of outside air conditions or wet bulb temperature, and then comparing a performance period to some sort of good baseline operating conditions. So we're always looking for whether we have some anomaly and are losing our performance. Over time, we're also getting more and more into compute side emissions. So we have done things like modulating compute cabinet fans on the compute side. NERSC pays a lot of attention to compute jobs, trying to make sure jobs complete, so we don't have wasted energy use on jobs that don't complete, and work like matching algorithms and hardware. So that's efficiency, and I'll just comment quickly on renewables and electrification, and we can move on. So renewables, I don't think of that primarily as a job for our compute center, but more of a site-wide strategy. You may have big open spaces where you can do renewable projects on site, or you may have ways, or you may be able to develop ways to procure renewable electricity. That's kind of the approach that we pursue here at Berkeley Lab with the Western Area Power Administration. In the third area, electrification, many of your supercomputing centers don't use much natural gas, likely, but you might have gas used for comfort heating. So in our facility, we're using waste heat from the computers to serve that comfort heating. Certainly one of the big opportunities we have is using all of the waste heat at your facility to replace natural gas at other parts on your site. Certainly in our case, at our lab, within the next few years, we anticipate that we're going to have so much waste heat from our computers that it could serve all of our natural gas loads 2 times over. That said, it's a challenging project to move that heat around the campus, but that's sort of one of the big opportunities associated with high performance computing, because you are producing so much waste heat. So with that, let's move on to the question and answer part. Jenna will take it from there. Thank you.
Sounds good. Yeah, thank you all. So as you can see, we're all kind of doing similar things, but a little bit differently at all the different national labs. So we have a couple questions in here, and they actually go pretty close to one of them. So our next question that we came up with was, what are scope 3 emissions for data centers? And we have a couple folks who also asked, are there any efforts to develop a standardized sustainability label for data centers? Or vendors during procurement. So I think we kind of can open that up to like procurement. Are there any sort of, what are the scope 3 emissions? And then what are, do we have any standards out there? So for this one, I don't know who wants to start, but I'll open it up to whoever wants to take a stab at that one.
I guess I could try. Are you able to hear me? I just switched back to my original speaker.
Yeah.
So the question, I believe here, is what are scope 3 emissions for data centers? I think there's kind of 2 questions here. What are the scope 3 emissions that we report, and what are the real scope 3 emissions? So what we often are reporting in our greenhouse gas registries are operational emissions. And so for scope 3, that means primarily the emissions associated with commutes and airline flights, associated with the individuals that are associated with your compute center. And that's relatively small compared to the emissions, the operational emissions associated with that center's electricity consumption. So we're reporting very few scope 3 emissions associated with HPC centers. As Carol Jean mentioned, The big scope 3 emission there is the embodied emissions associated with all of the equipment. We've done a very preliminary analysis looking at embodied emissions across our site and including across NERSC. And generally, it looks like the embodied emissions associated, mostly associated with the computers themselves, is in the same ballpark as the operational emissions that we're reporting each year. So all of those things that Carol Jean talked about, sort of moving to really understanding and making decisions about how to construct these centers is really the most important way to affect scope 3 emissions.
Otto or Jesse, do you want to add?
Yeah, I can add briefly. So similar to John, we report one thing and we are responsible for something that is probably far larger, right? So just based on our procurement, we expect our actual scope 3 emissions to be maybe a third more of our total, somewhere around 500,000 metric tons per year. And we expect maybe 170,000 metric tons once we fully account for scope 3. And that's just based on kind of the procurement methodology of looking at what comes out of procurement and what pounds per dollar there are. So it's a really kind of rough measure. But one challenge that we do have with our kind of scope 3 emissions that some of the folks on the call might have, maybe others don't, is that being a national security an NSA lab and having a computer that is a classified system, we can't reuse a lot of the parts that are in it. We have wholesalers that will come in and take some of the parts, but a lot of it just, by law, by practice, has to be disposed of. And so that really, as these computers get larger, that really affects our scope 3 emissions. Each one is bigger than the last. And so I think we really need to do a good job of figuring out what those scope 3 emissions are and what parts we can reuse, and then taking credit for those, because we don't want it all to end up in the landfill just from a waste perspective, but also from a carbon perspective. I also think that as things switch over to more kind of like GPU based computing, there's more embodied carbon in the manufacture of those, but maybe less so per flop. And so I don't have a good idea of like how that pencils out in terms of our total scope 3 emissions, and scope 2 emissions for that matter. But it's something that that we really, I think, need to look more at in the coming years.
And I'll go next, Jenna, but mine's going to be pretty brief because my colleagues covered this really well. We're very similar to John. We're looking at scope 3 emissions, but really honestly don't have great answers on this. And I'll have to point out our keynote speaker, Dr. Wu, did a great job talking about this, and the scope 3 emissions and embodied carbon of all kinds of data center equipment. So I'll just leave it at that, since again, not much to add, and she covered that in a really great way.
Yeah, great. So there was one question, has anyone from our site asked vendors about carbon emission data during procurement?
So I'll go first, and I'm not necessarily excited about this answer, but it's no. We are all focused on performance, basically performance and cost, obviously. And we just got done purchasing our latest flagship system. I would think in the next round we probably would be asking that question, but no, we did not in our current system. John or Jesse?
To my knowledge, we haven't been asking that. We've been focusing on kind of life cycle operational characteristics.
I think that's a real challenge, and something that's so performance driven and with a limited set of vendors, is that you can't go out and pick like the most efficient one. You need to pick the platform that meets the specifications for the mission that it's trying to achieve. And so, we need to optimize the embodied emissions of those. But if the vendor isn't doing that or can't do that, that's a real constraint. And so that's why we since we know how much power these things are going to consume, we're very focused on the Scope 2 emissions and trying to minimize those as much as possible. But there's a very good chance that we'll run numbers on Scope 3 and find out that it was far larger than we were expecting, and that we really need to be pressing our vendors more on, how they deal with these. I think I'm hopeful that with CHIPS and Science Act passing and a lot of new manufacturing coming online, that there's going to be a lot more efficient manufacturing practices. But at the end of the day, you're turning, sand into computers. So it's a pretty energy intensive process. And so it's going to take a lot of energy. And hopefully as the grid greens in the places where they're building these facilities, that will help us a little bit. But I get anxious about leaving that in someone else's hands. And that's why Scope 2 is like something that we can really affect and change. And so we can wrap our hands around that. And that's kind of where we've focused a lot of our efforts.
Yeah, thank you all. So I know there's another question specifically about standard labeling for any sort of sustainability things. And I know we have that for a lot of electrical equipment and water use stuff. There's like Energy Star and things like that. But I don't know if there's anything specific for data centers. And I didn't know if anyone else had heard of anything.
Yeah, I'll start that and colleagues can finish. For more run-of-the-mill, consumer hardware, business data centers, there's certainly like Energy Star servers and things like that. But given that this is the HPC focused, there really isn't. But I think really the key is performance. And Jesse actually just talked about this. But ultimately getting into ultimate metrics, it's flops per watt. But really getting in there, getting towards that is being able to do as efficient as computing as possible, both energy wise and water wise, and waste heat reuse wise. And where I'm leading with that is the performance is really what dictates primarily the sustainability. For us, when we procure hardware, we talk about, not only performance, again, petaflops kind of thing, but also that it has to be cooled with warm water, being able to be cooled with very warm water, and providing warm discharge water leaving so we can reuse some of that water for space heat. So not a standardized thing, but you need to specify the performance in your procurement, again, petaflops wise, et cetera, and cooling system wise. I'll pass to whoever wants to go next.
I guess I just might add, you could consider it a downside that there aren't standard labels, but on the other side, because of the really close relationship between all of you as specifiers and the people that make these very specialized computing systems, you have a lot of ability to affect the design of these systems over a pretty rapid time frame. So making it clear what you're interested in, if you're interested in efficiency and other things like reduced Scope 3 emissions, I think there's a considerable opportunity to transform the market in a way that isn't really possible in the greater consumer market.
Great. All right, so we'll move on to another one that we have, kind of get away from Scope 3 a little bit. And this is one question that when we were talking about questions for this panel, we were like, ooh, this is going to be a fun one. So we might not have the answers to this one, but I think it's a good conversation starter. So one is, how do we report cloud emissions? So cloud computing, storing things in the cloud, how do we report those emissions? I don't know who wants to start.
I guess I'm happy to start. I mean, certainly when we report greenhouse gas emissions, or registries as they're often called, we're following protocols. And those protocols are designed to try and ensure that there's not double counting and that emissions are all sort of comprehensively reported. Generally, each reporter will define a boundary Most typically, those are kind of operationally defined boundaries. So you define all of the facilities that are within your operational control. Sometimes people can define these around financial control as well, but most often I see campuses like ours defining things around operational control. My first answer would be, from cloud computing, if you're taking the computing from your site and moving it up into the cloud, generally you're moving that out of your operational boundary into someone else's operational boundary. So it would go out of your registry and into somebody else's would be my first guess at the highest level. That doesn't mean that if you're moving things to the cloud, you can't pay attention to what those emissions are and what that vendor is doing to reduce their operational emissions, or supplying their centers from renewable sources and so forth. I think that's all I got on that one.
Yeah, and we purposely brought this up for OCP to be discussing this because we don't have the answer on this. I think it's a fascinating question. Agree. We report just like John does. Operational emissions. And we don't currently do any cloud-based computing, but we do cloud-based storage. So we do send some of our information to the cloud. So somewhere, some data center is using energy and resulting emissions for our storage in this case. And then we're exploring cloud-based computing also. So I don't have any additional things, but I think this is potentially a good topic for OCP to think about, is how do we treat this, because it's probably an important topic. And I'll stop there.
Parts are still being on order and being built. We're not going to get
for us. It's a really pressing question because I just had my migration overnight to Microsoft 365, and so all of a sudden my inbox is moved from maybe our local data center or parts of it to somewhere on Microsoft's cloud, right? And so similar to John and Otto, like, how do we account for that? From what I've heard from our folks that manage kind of that part of our network infrastructure, is that we don't, but there are tools that Microsoft provides that we can potentially use to help calculate some of those emissions. I will say that the trend for us, we were very on-site, compute based, like our data centers, everything was stored on site, a lot of security around that. We're moving more towards cloud computing, and they have big plans with migrations and more using more Azure services. And so I think we need to figure out if it's substantial enough to where we need to account for it more, or work with the vendor to see. There's a good chance that wherever Microsoft's data center is, it's more efficient than the one we have in a cleaner grid region too. And so I'm not necessarily heartbroken over moving those emissions, but I don't want to be disingenuous about it and say, look, we reduced our compute emissions by 10% because we just shifted them to someone else's balance sheet. And that's a challenge just in scope 3 in general, is like where you draw the line, and are you double counting? And my personal view is that, like, if we're causing someone to do this on our behalf, we should account for it in some form or fashion, and as long as it's compatible with the GHG protocol standards, like, we should be accounting for it more. But like John mentioned, we have a pretty narrow list of scope 3 things that we tend to report right now, and most of ours is employee commuting, and then air travel is number 2, and they're not insignificant, but we're missing a lot of things that are especially embodied carbon, but just the transportation, the upstream emissions of bringing goods to the site, and then the disposal of them is, we're missing all of that as well. And so I know that's more a broader comment on scope 3, but for cloud computing, it's only growing for us. And so we really need to figure out and work with our vendors, how do we calculate it, and then how do we optimize it as well?
Yeah, I think that's another big question for us. It's say we decide to move some of our compute jobs to a different facility somewhere else. Do we account for those emissions that's at a different computer? Say we run some jobs at NREL, does NREL count for them, or do we, because it's our job but their system? There's a bunch of questions that are in there of scope 3 and how we calculate everything. That's definitely going to be fun. All right, our last kind of canned question that we had is, what are the primary environmental constraints for the expansion of HPC? So this can go a little bit outside of our emission stuff, but I think, John, we'll start with you on this one.
Okay, I think my overall comment would be, I think in the past, we've mostly been concerned about the growing energy and greenhouse gas footprint associated with each HPC expansion. Although now we're in a world in which we are decarbonizing the electricity grid, and we are in California, which is on a path and is committed to decarbonizing the electricity grid fully by 2045. So I see people, and I think of environmental constraints as expressed through, for us, the California Environmental Quality Act, and the fact that we have to go out and do a public review of any big project. So I see people being less concerned about that energy footprint because the greenhouse gas footprint is decreasing. What I see people, and I think is sort of a bigger risk for us as we expand facilities, is that water consumption. So as we look at the expansion, you start getting into a situation where you could be doubling the water consumption of your site, and that's a very big concern, both environmentally and within our community. So that pushes us certainly to change technologies, for instance, using air-cooled heat exchangers instead of traditional cooling towers. And I think that is really going to drive, sort of design decisions, is more concern about water consumption over time.
I'll go next if you want, Jenna.
Yeah.
And to build on what John is saying, and I'm going to talk scope 1 and scope 2. Yeah, our scope 2 emissions, some exciting news in Colorado is we worked with our utility provider in Colorado, actually my colleague Susie Belmont, who's on this call, negotiated or helped negotiate a deal for 100% 24/7 carbon-free energy beginning in 2026, I believe. So to John's point, right now our current emissions are very much scope 2 dominated. In the not too distant future, that'll get way better, and that's super exciting. That goes way beyond just data centers, by the way. That's for all federal facilities in Colorado. Going back to my recurring theme, the water is also going to be our next big driver. The way you get to water use reduction, and again, this will be an upcoming session tomorrow, is being able to cool with warm water that you can create with dry coolers as opposed to cooling towers. So it goes into hardware specifications. You got to be able to cool with that very warm water. And then really the first and foremost, the recurring theme is heat reuse. If you can reuse that heat, then you don't have to reject it. First dry, obviously, and then wet. So another concern for this whole industry is to make sure that our hardware is going to be available that can use this very warm water cooling. And I'll mention just briefly ARPA-E, that's a Department of Energy research program, has an ongoing research program called Cooler Chips that's just getting going. But its focus is especially looking at how do we make our hardware so it can run at much warmer temperatures. Again, allowing warm water, dry-based cooling anywhere in the world, ultimately.
We're pretty similar, water being a primary concern, in New Mexico, kind of just having emerged from a mega drought and maybe going back into drought again. It's definitely a challenge, and we're fortunate that our HPC complex is served by reclaimed water. So that's 30 some odd million gallons of water that we are pulling. That's non-potable, but the next platform might be 3 or 4 times that. And do we have the capacity? Can we put the infrastructure in? Can we supply all of that water in a non-potable fashion is really kind of a challenge. I think if we do our work on scope 2, I am okay taking the energy hit on cooling with air-cooled and saving the water, because that's a primary concern for us here, is that we can put more solar panels out, but we can't make it rain more. And so I think it's a balance between dry cooling, and that's always a balance between energy and water. You know, you take a little bit of an efficiency hit on the cooling side of things, but we are also looking at reclaiming heat from our computing complex. It's in an area served by our central steam plant. And we're working on conceptual designs to reclaim some of that. And as Otto mentioned, you know, if you're not rejecting that heat, you're not using water for it, and you're saving water in addition to saving energy. So those are some of the bigger concerns, you know, like non-emissions related. It usually for us comes back to water. But again, like, we have a fairly old facility served by an even older central steam plant, so it's not going to be easy to integrate all of these systems, even though the buildings are close to each other. We've got a 75-year-old steam plant that's serving 3 million square feet or so that we're trying to decarbonize over time. And so I see HPC as an asset for that, but also it's going to be a challenge, and we know it's not going to be cheap either.
Awesome, thank you. I see two more questions in the chat, and they kind of went off what you just talked to. So we said, isn't going from evaporative cooling to dry air cooling just a shift where the water is used? Because air cooling uses more energy, which in turn could use more water, and that's true. Depending on the energy source, it definitely could. But I think Jesse kind of explained that for Lionel of why we're willing to take that hit. So I don't know if Otto or John, if you want to add anything else to that, or if you think that kind of covers that question.
Yeah, you know, I'll start. And thanks, Cosimo. That's a great question. I'll have to point out earlier in the chat, Cosimo leads an OCP heat reuse group, and he put a link in there. And obviously, heat reuse, like we've all talked about, is kind of the holy grail. And then we don't get into the other water use things. In the session tomorrow on water use, dry coolers do use more energy, electrical energy than cooling towers, but it's not that much. And compared to the energy use of our compute, it's a fairly small number. And like Jesse kind of just said, if our energy use is all 100% carbon free, it's probably not that big a deal, especially in water constrained areas.
All right, and then the last question, because I think we're almost out of time, is oil immersion cooling. Thoughts?
You know what? I'll start again. I think it's an interesting and viable technology. It's not done much in the HPC world yet. But the promise of it is that maybe you can achieve these higher temperatures that we're all talking about, just because of better heat transfer. And I'll point out, it's not just it's all immersion cooling, which can be 1-phase or 2-phase. So there is some promising 2-phase approaches. I think all of us right now are primarily cold plates based cooling, but at the end of the day, yeah, it's an interesting one, and I think probably the jury's still out what's going to be the dominant technology in the future. Right now, if you can get to the temperatures we're talking about with cold plates, that works very well also. So I'll stop there.
Have you looked at 2-phase cold plates?
There's certainly vendors out there that make 2-phase cold plates. Some might actually be beyond this call, but I think that's a really specific, interesting technology. There's a lot of interesting cooling technologies out there, but no, we have not specifically done 2-phase cold plate research. I think some other national labs have, if they want to speak up.
Or Jesse, anything to add on that one?
I think it's really a a sign of how far we've come that we're talking about like the heat transfer medium on the chips and liquids and not like hot aisle, cold aisle containment, you know, like we're really, if you think about how far this has come in the last decade or two, it's kind of wild to wrap your head around. Like we still have some older platforms that are doing aisle containment, but it's like, how can you squeeze the most out of the temperatures going to the chip and how many phases and what's the heat transfer medium? So that's a great sign to me as like a net zero person that the HPC folks are thinking about this and trying to squeeze it out. They also get more compute power out of it if they're able, you know, if they have power capacity limits. So like the less energy that goes to the non-compute load, the more, you know, fast computers they can put in. So I think that's a great sign that we're moving in that direction, and not having to go into data centers with huge old aisles just sucking air out and, you know, all of that. So
All right, great. Well, I think we maybe have time for one last one if anyone has any burning thoughts.
Jenna, there was one question that I don't know was covered, and that was about double counting on scope 3 from Ty Leggett. It's worth answering.
Oh, yeah. Sure. I think, Jesse, you kind of spoke on that. Do you want to start with that one?
yeah, so scope 3 is a bit tricky, and I think all three of us have kind of evaded it in one fashion or another because it's really difficult to calculate, and no one that I know of is really doing it like completely enough where I'd say like, yep, I'm going to copy their approach. So like at the end of the day, you know, we're going to end up counting some emissions twice, but if we are responsible for it, you know, if we order something and they ship it to our site, you know, they are counting the scope 1 emissions from their transport, but they shipped it on our behalf, right? So we should be responsible for some portion of that emissions, you know, pursuant to whatever the GHG protocol says it should be. And so we do have this bit of like, if you added all these scopes up, it would, you know, be greater than the total emissions of the system, right? Like it's more than the parts are more than the whole. But for us, if we are in that operational control boundary where we're causing these companies, these vendors to incur these emissions, you know, we're partially responsible or wholly responsible for that, depending on who you ask. And so how we continue to do that, continue to calculate it, I think scope 3 will evolve over time, especially as scope 2 shrinks. Like we don't pay as much attention to scope 3 right now because it is, you know, less than 15% of our emissions, and scope 2 is most of our emissions. But if we go to 100% CFE, all of a sudden scope 3 is like 90% of our emissions, right? And so then we really have a lot of work to do. And so that makes it a challenge, but it also is going to highlight the need to really pay closer attention to scope 3, how you calculate it and how you offset it, because we know we're going to need some amount of negative emissions or something to offset those things that we just can't get to zero.
Great, thank you. Any other thoughts from Otto and John?
Yeah, it certainly is a goal of the greenhouse gas protocols to avoid double counting. But as I think this is maybe a restatement of what Jesse said. Certainly, as you start going into the sources that aren't reported, like scope 3, it's very unclear where the boundaries are between entities, and there's going to need to be a lot more work to sort of figure out embodied emissions reporting to avoid substantial double counting.
For sure. And we're hoping to get more guidance on that, I think, as we keep going forward. So
that's right.
All right. Well, I just want to thank the panelists so much for their time and giving us some really good things to think about. So thanks, Otto, John, and Jesse for being here, and appreciate all the conversation and feedback.
Yep. Thanks, everyone. And thanks, Jenna, for facilitating this. Interesting and fun.
Yeah. Thank you.
Thanks, everyone.
Thanks, Jenna and team. Okay, our final session, an interesting one. The focus will be on HPC data center heat reuse, where essentially the goal will be to discuss fundamentals of repurposing wasted heat in order to further improve cooling efficiency. The session will be led by Thomas Eilscher. He's working as a research scientist at the Center for Information Services and High Performance Computing at TU Dresden. His research interests include energy measurement, data processing infrastructures, and performance analysis and optimization for HPC. Thanks again, Thomas, and over to you.
Well, thank you, Sid, for the introduction, and welcome to our final session for today on the data center heat reuse, and in specific the HPC heat reuse. And we have already heard quite a bit about heat reuse in the previous panel, so this gives me a great opportunity to introduce the topic in more detail. I actually don't have much to say. I leave that to the invited speaker. But I thought it was very interesting to hear from heat reuse even referred to as a holy grail, if I got that right, from the US centers, because often if you look at the topic, you can get the impression that the focus is more on the European sides. So here you hear a lot of projects from Scandinavia, from Germany, and from the Netherlands. And there's also European legislation on the way, the Energy Efficiency Directive, that targets, for instance, that every data center has to make a feasibility study for heat reuse. It's a little small steps towards focusing on heat reuse in the data centers, but at least it is an ongoing topic. Also, there is a German legislation that is following this European legislation that also pushes this, but it loses a lot of teeth during the legislative process, and due to some, counter lobbying. But anyways, this is an important topic, and but it is not a surefire success, right? So even if we have a lot of examples, these examples are often very individual solutions that are required, and that includes both the technical aspects, but also political aspects if you want to use the heat in something else than your own organization. And so this brings me to our invited speaker for today, who will showcase a success story for heat reuse and also a perspective for heat reuse. And I welcome Ivana Bartol for this session. She holds a bachelor and master on mechanical engineering from the University of Zagreb, with her focus on process, power, and thermal engineering. She is very well suited for this topic. And so she can talk about all the things that I, as a computer scientist, have no idea about. Very happy to have her here. And now she works as a research associate at TU Dresden on a project where heat reuse actually plays a very important role. And so without any further ado, welcome Ivana. And I hope you can share your screen. Wonderful. We can see your presentation.
Of course. Thank you, Thomas, for the lovely introduction. Good morning, good afternoon, and good evening to everybody present. I'm Ivana Bartol from Technical University Dresden, and today I'll present you with the reuse of data center waste heat that is a part of the IT Zauber project. This project specializes or is focused on operational optimization of energy efficient data centers through the use of digital twins. I'll mention more about the project itself a little bit later on, but for now, a little introduction of the TU Dresden data center. Its official name is Lehman Centrum, or the abbreviation LZR that will be mentioned in further slides. And it is a high-performance computer and storage complex for science and research. The high-performance computers are directly liquid-cooled with the inlet temperature of 35 degrees Celsius, which is considered warm water cooling. Data center, with its constant waste heat output, serves as a valuable and high-quality heat source. And its close proximity to district heating network inspired the concept of connecting these two sides, where data center would serve as a heat producer or heat generator, and district heating network would be recipient of the data center's waste heat. This simplified schema represents our system. Starting with the high-performance computers, they are either directly liquid cooled with the help of coolant distribution units, or are cooled with a combination of side coolers and coolant distribution units. The first principle, or the direct chip cooling, bases itself on heat rejection system that provides cooling energy that gets redistributed to the computer with the help of coolant distribution unit. And the second hybrid solution is based on heat rejection system providing cooling energy then gets supplied into the side coolers and into the coolant distribution units that later on either indirectly through air or directly through water cool the computers. The generated heat on the high-performance computers then gets partially reused by heat recovery system that supplies the data center building ventilation and heating system, and also supplies another neighboring building with thermal energy. The rest of the heat is rejected through heat rejection system. This system relies mostly on free cooling with the help of hybrid dry coolers with closed cooling circuits. The system is also well equipped with temperature, pressure, and volume flow sensors. From the sensor data, we were able to monitor the waste heat distribution for a period of a year. These metrics show the measurements from December of 2021 till November of 2022. In this period, most of the heat got rejected through heat rejection system, and only a small amount of waste heat was being used for ventilation and heating purposes to satisfy the demand of these two buildings. To be more exact, out of the 100% of electrical energy that entered the high-performance computer, 11% got dissipated, 78% got rejected through heat rejection system, and only 11% got reused by heat recovery system. To evaluate the system's efficiency, we will use these three metrics: power usage effectiveness, energy usage factor, and energy reusage effectiveness. Power usage effectiveness, or the PUE, is already pretty low, with PUE of 1 being the ideal scenario. And this is because the cooling infrastructure that doesn't use any energy extensive operations, and the heat rejection system relies mostly on free cooling. But the other two factors are what drive us or drive the need for a change in this system, because only 9% of total facility energy gets reused, or 11% of the IT equipment energy. Our planned solution is to connect all of the cooling infrastructure to the heat recovery system, and to connect the heat recovery system to district heating network with the implementation of a heat pump. In this case, PUE gets slightly reduced because heat rejection system will be mitigated. But the other two performance indicators will drastically increase, resulting in 89% of IT equipment energy being reused. The exact plan changes of the heat recovery system includes directly supplying not only data center building and one other building that was already mentioned, but the two other ones that are newly built neighboring buildings with thermal energy. Also, 3 heat pumps will be implemented. 3 1-megawatt heat pumps will be implemented. And we will supply the district heating network with the thermal energy. Other than changes on the heat recovery system, some changes on the IT equipment system are being planned as well. From our initial system, there was around 1,100 kilowatt potential waste heat. And by the end of 2024, there will be more than 2,000 kilowatts potential waste heat. That is direct result of adding new high-performance computers to our system, and also to connecting every part of cooling infrastructure to the heat recovery system. For example, this side cooler. From all these planned changes will result in this predicted waste heat distribution. We predicted the heat demand from these directly connected buildings and allocated the rest of the heat to a heat source of this heat pump. This predicted waste heat distribution will result in more than 19 gigawatt hours of thermal energy annually that will be supplied to district heating. This project prides itself with its holistic approach, and some of these remarks can support that claim. As of right now, more than 95% of heat generation for district heating is based on a concept of a combined heated power from natural gas. With the application of heat pump with free waste heat as a heat source, we would be one step closer to a sustainable future. Also, district heating networks, other than providing heat absorption and heat storage options, can serve as a heat supplier for the all connected buildings when their demand will be higher than the data center's waste heat, meaning that the energy can flow in both directions. Also, the cost of avoided heat rejection system would be significant, and the CO2 emissions would be reduced by more than 700,000 annually. And this only on account of avoiding the heat rejection system. And I'm sure a lot more would be avoided by on the district heating network side, because it won't rely only on combined power and heat plant. This project is a collaboration between multiple parties, one being Technical University Dresden, also University in Aachen, Romtechnik, and other associated partners. The project is focused on developing holistic energy systems that will maximize computing power while still ensuring the energy efficient infrastructure. By implementation of a digital twin as a state-of-the-art model representation, we hope to integrate data center into evolving system that will strive for optimization in all aspects of data center operations. Real-time simulations for assessing potential future scenarios will also allow easier decision-making process with the ultimate aim of sustainability and efficiency in mind. Also, this project optimizes data center operations while considering constraints of an increasingly renewable and volatile energy supply. That's it from me for today. Thank you for your attention, and I would also welcome all of your questions.
Thank you, Ivana, for the presentation. I'm trying to scroll through this chat. It always jumps around a little bit. There was a question from Masho Geni: is the server room air conditioned, and is the power consumption for air conditioned also accounted in the PUE? And this was already answered in the chat by Daniel Hackenberg with yes and yes. So the server room is air conditioned and it is being accounted for. The next question from Thomas Durbin. What is the minimum temperature required for the heated water to be useful? And I think this has to be answered for the near range heating on the same building and the adjacent building with a separate answer for the district heating, right?
Yes, so both of the adjacent buildings would use inlet temperatures from 45 to 50. Let's say 47 is our goal, and they use the low temperature heating and ventilation. But district heating would also need much higher temperatures, coming at around 90 degrees Celsius. And this is the exact reason why we would need to implement a heat pump to bring the temperatures from 47 to 90.
So I think this is in line with the next two questions from Herbert Huber and Michael Ott, who are asking about the power consumption of the 3 1 megawatt heat pumps, as well as the EER for the heat pumps, considering the temperature change from 45 degrees Celsius to 90 degrees Celsius, which are obviously not free, yes.
Yes, this was a big discussion in our project, but according to the ISO norm 3134, any equipment that is on the side whose purpose is heat enhancement of waste heat shouldn't be accounted in the key performance indicators of this data center. So there is a considerable power consumption of this heat pump, but it should not be a part of the PUE of the data center, because this heat pump only enhances waste heat.
So this answers the question for the metrics, but do you already know the EER for the heat pumps, or is this something that's not yet finalized?
I do know, and this is the metric that I use to calculate the potential district heating. So the heat that goes from heat pump to district heating, and it is around 5.099, if I'm not mistaken.
Okay, I think Daniel stated that the COP is something like 3. Now, I'm not sure if this is perfectly in line.
Yeah, I would have to check, but I would be surprised about a PUE, a COP high like that. And I would like to mention, because there was a question, if there's a data center room cooling and if it's accounted for in PUE, and the answer here was somewhat was regarding the heat pump, not regarding the data center cooling. Everything that's about data center cooling, including the air conditioning of the server room, is part of the PUE. I wanted to explicitly state that.
Yes, thank you for clarifying that, Daniel. Maybe you can also...
So maybe I can answer the next question as well. Yes, somebody will have to pay the electrical bill. That is our provider of the district heating system. And if that's competitive or not is always a question of the price of the natural gas. And my guess is as good as yours, or probably worse, what the price of the natural gas in the coming years is. We cannot calculate this based on today's prices. We can all build Excel sheets and then extrapolate, and we can push these sheets in any direction depending on the price of the gas. I hope the price will be very high, because I hope there will be a high CO2 price on it, but this is basically not predictable because it's part of the political process, right? It is competitive enough for the district heating provider to do this project. even though they get some EU funding, I think, for building the heat pumps, but I'm not perfectly sure about their agreements. I hope this answers the question.
I think it does. There was also a question, maybe we can answer it together. What is done with the heat in the summer where we don't have to heat the rooms? And I think one of the answers is water. So just water that's consumed for showering, etc. And maybe Ivana or maybe Daniel, you have a better answer also with what is done in the summer with the heat in the district heating.
Would you like
Well,
to, Ivan? I can do it as well.
Well, my guess is that this district heating has a lot of storage options that can store the heat, or if another companies are also connected to district heating, that could be use waste heat for production processes.
Yeah, basically the advantage, this is the advantage of having a district heating system attached, right? So not small, meaning a couple of houses nearby, but really a district heating system that covers basically the city of Dresden. So the answer, showering water is sufficient for the amount of heat that comes out of our supercomputer center. They would have taken more. Yes.
So if you live in Dresden and in the southern area, you often drive by one of the heating plants. And so you see the big towers, the big stacks that are burning gas to do the heating. And so this is always a reminder, if we can replace the gas that's burned there, it will be helpful regardless of the season. Let me scroll through the questions. This is a very good, lively discussion here. Another very interesting question is actually from Matt Kukul. How are increasing chip power densities, lower T-case requirements factored into the simulation, as the presentation shows 35 degrees Celsius to what would be a CDU prior to distributing the liquid to the chip? And I'm going to direct the question to you, Daniel, because I know that you have an opinion about the Ashari temperature requirements, and I think this goes in this direction.
Yes, that is true. Yes, this is actually part of the project. So I'm not perfectly sure how well we will be able to do this. I know that there's been work done in the past, thinking about whether we use this temperature at the chip or that temperature at the chip. How do we increase or decrease the efficiency of the chip itself? So it would be nice to include this into the simulation so that we could actually say, try to find an optimum there. What temperature exactly we have at the chip is basically depending on the specific system configuration, right? It is correct that obviously this will be higher than the 35C because this is prior to the CDU. And then we have a higher temperature on the other side, high at the CPU itself.
Okay. Yeah, good.
Yeah, you mentioned ASHRAE, and yes, quite a few people have an opinion regarding the recent ASHRAE requirements that basically tell us to reinstall chillers. We are not planning to reinstall chillers. That's true.
Daniel, thanks for your comments. As the chair for ASHRAE TC99, I appreciate hearing feedback like that, so we can take that to our various different groups. I wanted to get your opinion and the group's opinion on that, just because it's a topic. It's definitely something that we're seeing. It's definitely something that we're, as a design professional, seeing throughout the industry and lots of discussion about. So appreciate your feedback and comments.
Yeah, basically, if I can add one thing, what I'm always wondering is what is the next step? Like, where does this end? So if we reduce the temperatures now, it's not like we hit some magical temperature where later on all future processors with growing power densities will be okay with that temperature. And I hopefully we don't end up in a future where we need some nitrogen or something like that to cool our computers. So basically, it's a question of where do we don't want to stop with this downward temperature curve. That would be my question there. And I would hope that it's a temperature that can be still free cooled in the majority of regions that have these computers.
Yeah, I think that's a great question, and luckily we've got Silicon guys sitting on ASHRAE TC99 to help kind of give some feedback on that. So more to come, I think, is the short answer on that. So thanks for your question and comment.
Okay. There was also a comment about low temperature district heating, and I just want to resonate on that, because in my research on the current discussions, especially in the political spectrum, this is a very strong focus on how to shift the investment costs in the data center heat reuse on a political scale, because if you want to have a lower temperature district heating, this means investments for the utility providers. And if you want to have higher, higher temperature, then this means investment in the heat pumps, and of course investment in the electricity for the heat pumps. So there is a balance to be found there. And I think 90 degrees is already not the craziest one. I've heard of requiring 100 degree. So, well, I guess, but there are certainly lower proposals as well. So, well, thank you for the discussion already. We had planned initially to have a second speaker, but there was this didn't work out. So we have now a little bit more time for an open-ended discussion on the topic of heat reuse. And so if you have a little story to share, or you want to use a soapbox to present something that blocks your data center to reuse the heat, for instance, you feel like there's some technical limitation that needs to be overcome, or you feel like there is a organizational political thing that needs to be addressed to utilize all of the heat that we are generating in our data centers, then feel free to raise your hand or jump in.
Well, I mean,
also,
I can comment.
Yeah, good.
I can comment
Sure.
if you want, Thomas. As Otto mentioned, at the OCP, we have a devoted heat reuse group, and we have been looking at these applications for a while. And I left that comment about the fifth generation district heating, but there are other uses for the heat that are not human comfort that are probably a better fit, because they are 365 days, and one of them, for instance, is in industrial laundries, and laundries they use a lot of heat year round, all the time. And there's like hospitals, there are few applications. Unfortunately, that means that there needs to be some coordination between the data center operator or owner and the city, and that, on our opinion, that is one of the biggest challenge at the moment, putting all the actors together around the table.
Yes. So Dale Soto, do you want to add something to that?
Well, I wanted to add something to the ASHRAE discussions. I think there's a couple of old timers here. Shlomo will probably back me up that it's been decades that ASHRAE's been predicting that we're going to need chillers for data centers. And I think it's up to us as users to continue the push for non-compressor based cooling of data centers, because it's not a technical impossibility. It's a desire. Obviously, the cooler your fluid, whether it be air or water, the easier it is to cool dense computing, but it's not impossible to cool it with warmer temperatures.
Yeah, but you may not have a choice in the future, Dale. I mean, it has to do with Intel, AMD, and all those other guys. I mean, it's not up to us.
And NVIDIA.
And NVIDIA, of course, all the guys.
Okay, maybe some other questions to where the research focus on this topic should be, maybe for the mechanical engineering, anything specific. Otherwise, we can also, oh, Herb, seen.
You, having owned 21 energy plants providing district heating and cooling to 11 cities in the US, I can tell you that it's a pretty poor match between adding heat pumps to bring the temperatures up to where they need to be for district heating and cooling is a expensive and unproductive solution to the problem. A better solution would be water source heat pumps circulating tepid water, groundwater temperature possibly, to a district energy system that supplies this groundwater to water source heat pumps in buildings at the edge of the network. And each of these buildings would have one piece of capital equipment would provide both heating and cooling for the buildings. It's a better solution in my mind. Liquid Cool Solutions, which a company I currently am the vice chairman of, it's a rack-based single-phase immersion technology with what we call directed flow. It's all patented, and we can cool processors adequately with inlet energy, water temperature of 45 C, and we consume no water actually if it's cooler than 45 C outside, dry bulb. And so it's a pretty good solution. It's rack-based, so it's easy to convert from air to liquid by simply replacing servers. We have to modify the racks a bit, replacing servers as old ones are being refreshed. So I would just suggest people might want to look at Liquid Cool Solutions, alloneword.com. I'll put it in the chat if you're interested.
Sure, please do. Okay. So I don't see any more immediate hands up. And so I would like to thank everyone for the discussion again, and I will give it back to Sid to close out the day.
Sid, I think you might be muted.
Yes, I am muted. Sorry about that. Firstly, thanks, Thomas, for the engaging discussion. And a few quick logistics. Tomorrow, two interesting talks lined up, two sessions. First is on water conservation in HPC, where focus will be on discussing the challenges and lessons learned with regards to efficiently using water for making future data centers more resilient. And the next session will be on HPC modular data centers, where really the focus is on different experiences and lessons learned in planning, building, and operating an HPC center using a modular approach, right? And then we'll, of course, also give quick highlights about upcoming events. And one final note is a workshop website. Again, please take a note of this. We will be uploading the recordings and the our presentation slides soon. Please do consider joining the many ongoing sub-teams. Contact information, person of contact is Natalie. And again, Torsten and I, we would like to thank the workshop committee and all the other presenters and moderators and speakers for today. And with that, it's a wrap. Thanks, folks.
Thanks, everyone. Great presentations. Thank you.
Great. Thanks, everybody.
Thank you. Thank you.
Thanks, everybody. See you tomorrow. Bye.
Great job. Thanks.